Hello viewers, it is Professor T. N. Oza here. As a part of our continued effort to teach undergraduate and postgraduate students about spectrometry, I am going to discuss some aspects of infrared vibrational spectrometry today. As we know, molecules of all substances in all physical phases are ceaselessly vibrating, that is to say, executing to and fro bond stretching motions and bond angle bending or shape deformation motions. These motions are called fundamental vibrations. If a molecule has n atoms in it, so for n atomic molecules, there are possible maximum of n minus 1 bond stretching and 2n minus 5 bond bending fundamental modes of vibrations. Absorption of infrared radiation by molecules leads to the excitation of their vibrational quantum states. These quantum states are defined by the vibrational quantum number, symbol small v, having integral values 0, 1, 2, 3, etc. etc. The measurement of these absorption frequencies constitutes infrared vibrational spectrometry. It provides useful information about the functional group present in the molecule, about the structural possibilities, structural fragments, about rate of reactions, about tautomerism of compounds, and also about molecular weight of polymers. More importantly, this infrared vibrational spectrometry is useful to show the identity or non-identity of two samples. Actually, this technique is very useful for forensic science, crime investigations, and for those persons who are working in the field of natural products chemistry. When a new product is isolated, identity with the authentic sample is required to confirm its structure. The infrared vibrational spectra are generally studied in the region 4000 to 667 reciprocal centimeter, occasionally up to 50 reciprocal centimeter for coordination compounds. So I have given an outline of the technique. Infrared spectroscopy is very simple to interpret and it is very common for chemical laboratories, for research laboratories, or chemical process industries, forensic science, and many other sciences wherever chemicals are to be studied. The vibrational energies of infrared radiation and the vibrational energy of molecules, they are comparable. Actually, the vibrational energies of molecules compare favorably with the middle infrared region, that is tending from 4000 to 667 reciprocal centimeter. For a diatomic molecule, the vibrational stretching wave number is given by the classical formula which reads as 1 by 2 pi c multiplied by under root of k by mu in the units of centimeter inverse. Here in this expression, k is force constant of the chemical bond and mu is reduced mass. What is force constant? The resistance of a bond to stretching is called force constant. Triple bonds have more k value than double bonds than single bonds. More polar a bond is, more is the value of k. If the bond is connected between its lighter atoms, then mu value is more, therefore the frequency value is also more. Mu is reduced mass. What is reduced mass? Suppose we have a molecule of the type AB, two atoms, atom A and atom B. And how do we calculate the reduced mass? Mass of atom A multiplied by mass of atom B divided by sum of both masses. And how do we calculate atomic mass? It is calculated by dividing atomic weight with Avogadro's number. So clear cut, there is a distinction between atomic mass and atomic weight. When atomic weight is divided by Avogadro number, we get mass of one atom called atomic mass. And in this way, mu AB, which relates to the reduced mass of the system AB, can be calculated. Transitions can occur between adjacent vibrational energy states. What I mean to say, if a molecule absorbs infrared radiation, then it gets vibrationally excited. The selection rules state that if a molecule is present in the quantum level V, then by absorption of energy, it will go to the next higher level, that is V plus 1 level. Alternatively, if a molecule emits energy and it is present in the V level initially, then it will come down to one lower level, V minus 1 level. These restrictions are called the selection rules. How do we calculate energy of photon? Whether it is infrared radiation or UV radiation or visible radiation. The formula for the calculation of energy is the same, and we are expected to be quite familiar with the formulations. Energy per photon, that is energy for a single photon, is equal to h nu, where h is Planck's constant having value 6.626 times 10 to the power minus 34 in the units of joule second. Nu is frequency in the unit of per second or hertz or cycle per second. Then Hc lambda is also equal to h nu. Here lambda is wavelength in centimeter units and c is speed of light again in the centimeter units, value 3 multiplied by 10 to the power 10 centimeter per second. If you want to be more accurate, value of c is 2.9979 into 10 to the power 10 centimeter per second. Another expression is hcy lambda equal to hc nu bar. Here nu bar depicts wave number in units of reciprocal centimeter. Wave number and lambda are inversely related. Now if we want to calculate energy per mole, the above expression has to be multiplied by Avogadro number. That is all. The value of Avogadro number is 6.022 into 10 to the power 23 per mole. Now, what are the conditions for the absorption of infrared radiation? This is to be noted that all vibrational modes of a molecule need not necessarily absorb infrared radiation. Some modes may be infrared active, some may not be active. What are the conditions we are going to discuss now? Only those vibrational modes are infrared active which are accompanied by an oscillating dipole. The sample is scanned through 4000 reciprocal centimeter, 667 reciprocal centimeter, or even down, and the result is presented as a 2D graph, two-dimensional graph. The wave number scale is shown along the horizontal axis from 4000 to 667 reciprocal centimeter, and the intensity of absorption A is shown along the vertical axis. Absorbance A is defined by decadic log I0 by IT equal to epsilon Cv. What is this I0 and what is IT? The incident radiation which is used for recording the spectrum, the initial intensity is called I0. and after traversing through the sample, the transmitted intensity is called IT. Then the decadic log I0 by IT defines absorbance, which is also equal to epsilon Cb. It is the familiar Lambert-Beer law. Here C refers to the molar concentration of the solution sample, which is filled in the tube of width B, and epsilon is the molar absorptivity, the characteristic of the functional nature of the compound. Here I must tell you, sometimes instead of absorbance, percent transmittance is used, is the variable. Percent transmittance equal to 100 multiplied by IT by I0. One more thing I want to make clear here. This Lambert-Beer law expression is more commonly used when we are dealing with solution, particularly for electronic spectrometry. For infrared spectrometry, we generally don't bother much about the concentration and the Lambert-Beer law because we are interested in having a qualitative spectrum from which functional group can be identified. So these things I have just narrated because they are useful. The concept should be known. Now, as I told earlier, molecules are continuously vibrating. Mainly, two types of vibrations are known. One is called bond stretching vibration, and the other one is called bond bending vibration. What is the meaning of bond stretching vibration? The rhythmical extension and shrinking of chemical bonds symmetrically or asymmetrically, such that bond distance R increases and decreases in succession from the equilibrium value Re. Now suppose we are having a molecule which has n atoms in linear shape, then there will be a maximum of n minus 1 fundamental stretching modes. Examples: CO molecule or HCl molecule, both are diatomic. So if I use the formula n minus 1, where n is equal to 2, a single stretching vibration occurs. Or a triatomic molecule like carbon dioxide, which is also linear, the formula says two stretching vibrations will be found, symmetric and antisymmetric. Usually, the antisymmetric vibration has a bit higher energy than symmetric one. Similar is the case for non-linear triatomic molecules like water, also shows two stretching vibrations, symmetric and antisymmetric. Here I should tell you, for carbon dioxide, the antisymmetric stretching vibration is IR active because it is accompanied by a change in the dipole moment of the molecule during vibration. But the symmetric stretching vibration does not involve any change in the dipole, therefore it is IR inactive. However, this mode is Raman active. When we study Raman spectrometry at a later stage, then I will explain to you why for centrosymmetric molecules, the IR inactive vibrations are necessarily Raman active and vice versa. Again, I repeat this point. If a molecule possesses center of symmetry, then those vibrations which are found to be IR active will be Raman inactive, and those vibrations which are found to be IR inactive will be Raman active. So the condition for absorption, as I told here, mathematically it is written like d mu over dx not equal to 0. Here d mu refers to infinitesimally small change in dipole moment with respect to infinitesimally small change in the distance parameter dx. If this condition is fulfilled, then absorption of IR energy is possible, otherwise not. The next type of vibration is bond bending vibration. The bond bending changes the shape of the molecule. Therefore, it is also called deformation vibration. If there are n atoms present in the molecule, there will be a maximum of 2n minus 4 fundamental bond angle bending vibrational modes if the shape is linear. It may be noted that very few molecules are linear. Majority of the molecules are non-linear, and for non-linear molecules, 2n minus 5 fundamental bending modes of vibration are possible. This is the maximum number. Not necessarily all modes are independent. Sometimes 2 or 3 modes may be degenerate, that is having equal energy. Condition for absorption of IR energy during bending vibration is like that for stretching vibration. Mathematically it is written d mu by d theta not equal to 0. Again, mu is dipole moment. D mu means infinitesimally small change in dipole moment, and d theta means infinitesimally small change in the bond angle. Examples: diatomic molecules like CO, HCl, we have the formula 2n minus 4 equal to 0. No bond angle bending vibration can take place for diatomic molecule. If the molecule is triatomic and linear, like CO2, then the formula 2n minus 4 is applicable. It gives two bond angle bending modes. For carbon dioxide, at a later stage I will show the means of diagram. Two bending modes are possible. Both are IR active, but energetically both are the same, equal. Such situation is described by saying they are doubly degenerate modes. Means the instrument experiences only one frequency. Theoretically, we have two frequencies. If the molecule is non-linear and triatomic, then bending modes will be 1. The formula says 2n minus 5 equal to 1. So for non-linear triatomic molecule, there will be 2 stretching vibrations and 1 bending mode. Here I have given some examples: carbon monoxide, carbon dioxide, water, ammonia, and CH3C. For carbon monoxide, number of atoms is 2, so number of bond stretching mode is 1. The formula is n minus 1. For CO2, n equal to 3 atoms, shape linear. So 1 IR active stretching, which is antisymmetric, 1 IR inactive stretching, which is symmetric, and 2 degenerate bending modes. For water molecule, number of atoms is 3, number of stretching 2, both active, number of bendings 2n minus 5 equal to 1, IR active. For pyramidal shape ammonia molecule, number of atoms is 4, 3 stretches, 1 symmetric and 2 degenerate antisymmetric stretches, 4 bendings. For molecules containing more than 3 atoms, bendings could be in plane and out of plane. Here, note down, mathematically, if there are only 3 points, they can never be non-planar. They must always be planar only. So if the number of atoms present in the molecule is 3, out of plane vibrations cannot take place. When the number of atoms present in the molecule is more than 3, then basically 2 types of bendings take place. One is called in-plane bending, which is of 2 types: scissoring, rocking. And the other one is called out-of-plane bending, which is again 2 types: wagging and twisting. For practice, we have taken up some examples: carbon monoxide, carbon dioxide, water, ammonia. Here one very important point I want to raise. For carbon dioxide, there are two stretching vibrations and two degenerate bending modes. The machine IR spectrometer will pick up only two frequencies, the antisymmetric stretching and the bending. But if we are to calculate 0 point energy, then all four vibrations should be taken into account. The energies for all those vibrations should be added up. Now, let us consider triatomic molecule. I will try to show you how do we derive the formula 3n minus 5 or 3n minus 6. Simple logic will explain how do we get this formula. Suppose you have one atom. It can move along x direction, along y direction, along z direction. That is, for one single atom, we have 3 degrees of freedom. Suppose the molecule has n atoms, then theoretically it should have 3n degrees of freedom. By logic, we can explain the number of freedom is less, 3n minus 5 for linear molecules, 3n minus 6 for non-linear molecules. How do we derive at this conclusion? That has been explained in this slide. Suppose molecule is A, B, C, where A and C are the terminal atoms. Now, if A is moving along plus x direction and C is going along minus x direction, this will be stretching mode. But if A and C both are moving either in the plus s direction or minus x direction, either in plus y direction or minus y direction, either in plus z or in plus z direction, then all these motions are not vibrations. For a motion to be classified as vibration, what is necessary? Either the bond length should change or the angle should change. If neither bond length changes nor angle changes, this motion cannot be a vibrational motion. It could be either whole body translation or rotation. Here I have nicely explained that out of 3n possible fundamental modes, 3 will be translations of the whole body and 2 will be rotations, not vibrations. Suppose both atoms A and C are moving in the same direction, plus x or plus y or plus z, then these three modes will be whole body translations, not quantized, not vibrations. These are simple translations. Now, suppose A and C atoms, which are terminal atoms, are moving perpendicularly to the molecular axis in opposite directions. Suppose A is going along plus y and C is going along minus y, or along plus z and minus z. These motions are whole body rotations, not vibrations, because neither the bond length is changing or the bond angle is changing. So we have to subtract 5 from 3n. Thus, for a linear n atomic molecule, how many fundamental vibrations are possible? 3n minus 5. Similarly, if the molecule is non-linear, then there will be 3 translations and 3 rotations. So the net number becomes 3n minus 6 fundamental vibrations. Some of these vibrations may be degenerate. Another very important term is overtone vibrations and combination vibrations, combination bands. When we record infrared spectrum, we get very large number of absorption peaks. Some peaks are due to fundamental vibrations. Some very small peaks are also due to some other regions. Then I will explain you what is overtone vibration. Overtone means two identical frequencies, they undergo constructive interference. Then the band appears at twice or at thrice the original frequency. Such such incidents are very rare, have very low probability, but they are often present there. And in some cases, particularly in the case of aromatic compounds, they provide some useful information. What are combination bands? Suppose two bands get set up, nu 1 and nu 2, or 3 nu 1 minus nu 2, etc. So all these are non-fundamental vibrations. Fundamental vibrations are those which are according to the formula 3n minus 5 or 3n minus 6. Some other bands appearing due to multiplication of one frequency or addition of two frequency or addition of three frequency minus some frequency. These type of bands are called non-fundamental. They have low probability and sometimes they provide some useful hint regarding the structure of the molecule. Here in this slide, I have shown Morse potential. You see very clearly when two atoms come closer for forming a bond, then the potential energy decreases until it goes to a minimum, and that is the bonding situation. If you bring the atoms closer further, then the energy rises due to repulsion between their electronic clouds. So here dE refers to the bond strength, R is the bond axis, and the 0 point axis of energy is shown. Up energy is rising, down energy is decreasing. Here I have shown you the figurative meaning of various kinds of fundamental vibrations for the linear molecule A, B, C. The symmetric stretching is shown like this. It has two kind of symbols. Some authors prefer nu S, S for symmetry, nu for frequency. Some authors call it nu 1 band. The antisymmetric one has been shown clearly. One bond is elongating, the other one is constricting. So this asymmetric mode is called nu A for asymmetric, or nu 3. Then the bending mode is also shown. The terminal atoms are moving like the scissor, kainchi, in the XY plane. This is called symmetric bending or deformation or scissoring. In the lower diagram, the positive sign put over atoms A and C indicates they are moving in front of the plane of the paper. So this is also scissoring because 3 points can never be non-planar. They are always in one plane. So both these modes, which are shown on the right hand side, though they are looking different, they involve the same amount of energy. Therefore, they are called degenerate modes. In this diagram, I have shown the Hooke's law potential. I will explain you to this diagram. X indicates the displacement from the equilibrium position. At equilibrium position, displacement x equal to 0. At this position, the kinetic energy of the system is maximum. When it is displaced, the two extremes shown on the graph, at the extreme point, kinetic energy becomes minimum, 0, and while this potential energy becomes maximum. At x equal to 0, potential energy is minimum or 0. So this graph nicely explains the change of potential energy with respect to displacement x. Now, certain assumptions have been made while deriving this Hooke's law potential equation. What are these assumptions? a point mass m. Point mass means it is a particle without any volume. Although this is not possible, this is just impossible thing, but for mathematical brevity or mathematical convenience, we assume that it is a point mass, having only mass, no volume. Second assumption, again, very jokey one. The spring with which the atom M is suspended is weightless. As we know, a spring can never be weightless. But for mathematical convenience, we have to accept this. It is when the atom M is made to undergo undamped oscillation to and fro about the equilibrium position, that is x equal to 0, then the restoring force F, which tends to bring it into the equilibrium position, is equal to minus kx. Here k is called restoring force constant, x is displacement from the equilibrium position. Work done is minus f dx. Now putting the value of f, we get k times x dx. Now the rate of change of potential V with reference to x with respect to displacement is given by dV by dx. Now we can obtain the equation potential as a function of x equal to 1 by 2 kx square. Simple integration of the above expression. Note that the potential is twice that of kx square. Here this diagram taken from my own book indicates three very significant points. First point, the dotted line shows the vibrational energy states should be equidistantly placed. This curve is for the harmonic oscillator model, which is not correct model for a molecule. Molecule is not harmonic oscillator, it is anharmonic. But for mathematical simplicity, we assume it to be harmonic and then apply corrections for anharmonicity. The thick line shows the graph, potential energy graph for the anharmonic oscillation or a real molecule. Here this symbol dE indicates dissociation energy. If the vibrational level reaches to that point, then the molecule will break away. A very significant point in this graph is that we earlier studied rotational spectroscopy. There I had narrated if a molecule is lying in its zeroth rotational quantum status, then its rotational energy will be 0. But here for vibrational, even if a molecule is present in its lowermost quantum level, that is V equal to 0, then its energy is not 0. Instead, its energy is ZP, 0 point energy, and this is equal to half hc nu bar. H Planck constant, c speed of light, and nu bar 0 is the fundamental frequency of vibration. So this emergence of 0 point energy is the application of quantum mechanics to the derivation of energy of vibration. Classical mechanics does not tell about this. The classical mechanics also has another deficiency. It says that the molecule will never break, the energy will go up and up. But application of quantum mechanics says that beyond a certain position, the vibrational levels will coalesce, there will be continuum, and the molecule will break. Here, I have again taken this diagram from my own book. I have shown the various vibrational modes or few molecules, or water molecule which is non-linear, 3 atomic molecule. The formula says total 3n minus 6 equal to 3 modes. New asymmetric, delta scissoring, and new symmetric. If we are asked to calculate 0 point energy, we will have to add these three values to get the 0 point energy of the molecule. For methyl group connected to a carbon, because the number of atoms is more than 3, in this case, both in-plane and out-of-plane vibrations are possible. You see, the diagram nicely explains what is the meaning of in-plane and out-of-plane vibrations. The values are also given. Yet another example I have taken, carbon dioxide, linear triatomic molecule. As I told earlier, one symmetric stretching, one antisymmetric stretching. Antisymmetric stretching is IR active, symmetric one is IR inactive, and two degenerate bending modes. Here two important points I should tell you. Firstly, in the diagram, there is a small mistake. The atom O going away from C, it should be coming inside in the first diagram. Please make this correction in your notes. If we are asked to calculate 0 point energy of carbon dioxide molecule, then we have to include 4 points. Value for symmetric stretching, value for antisymmetric stretching, and twice the value for bending, because bending vibration is doubly degenerate. So if we are asked to calculate 0 point vibrational energy for carbon dioxide, then we will have to add 4 data. Asymmetric stretching, symmetric stretching, and bending stretching, again bending stretching, bending mode. In this slide, I have given the force constant values, the vibrational frequency data for some compounds. Some inferences can be drawn. When the bond is 3, triple bond, then K value is very large. Accordingly, the vibrational frequency is also large. First one, triple bond higher than double bond, higher than single bond. Second point, if a bond is more polar, then K value is high. Also the frequency is high. OH for example. C double bond O for example. You can compare C triple bond O and C triple bond C. One is polar, one is non-polar. Non-polar has lower K value and lower frequency of absorption. The third conclusion is, if one or both atom is lighter atom, like CH, then frequency is more. If you replace H by Cl, frequency goes down. So, by means of these slides, I have covered some aspects of infrared vibrational spectrometry. This is not all. I will cover up this chapter in 3 to 4 parts. I hope this much you must have followed. If you make 1 or 2 readings, then you will certainly follow the gist. In coming videos, I will take up other steps which have remained. The chapter is very large one, but very, very important. And students should develop mastery over this spectroscopic technique, because this is very commonly used both in chemical process industries, in research laboratories, and these days spectroscopy has become talk of the day. It is used not only in chemistry, biochemistry, pharmacy, chemical engineering, almost everywhere where chemicals are involved, spectroscopy is there. So I hope you will learn some points from this video, and you will collect other informations from relevant sources. Thank you very much. I wish you success in future.